Reject. Question number 3, ring on rock. Reject. Okay. Question number 8, equipotential line. Be a set.
Problem number 8, equipotential lines. Okay, so problem statement says that placing electrodes in water supply the same voltage and use a voltmeter to determine the electric potential at various locations. Investigate how the measured equipotential line deviates from your expectations for different conditions and liquids. And I think there are 3 key questions. What does the voltmeter measure in the solution? What parameters affect the potential in the solution? And how do these parameters affect electric potential? So this is our legal context. Before we jump into our experimental setup, we need to understand what a voltmeter measures. So a voltmeter measures the tendency of ions to move, and whether that motion is caused by electrical or non-electrical forces doesn't matter. And also, the current that is flowing through the voltmeter is very, very small. And it's on a scale of nano to microamps, which is small compared to the total amount of ions in the solution. And we have 3 experimental setups. This is our first setup for measuring the potential at different points. And we have an Arduino Uno and a variable resistor that supplies the voltage. And in order to measure the voltage at different points, we have 6 analog pins. And these pins measure the voltage with respect to the reference electrode, also known as the cathode. And we have 7 notches in total. So after measuring the potential of this notch, we'll move it to a different location. And after completing 3 sweeps through all the notches, we will take the average of the voltage at each point for our experimental data. And the experimental setup too is to measure how the equipotential line changes with respect to time. So the measured pins are numbered pin 0 to pin 5. Pin 0 is the pin closest to 0 volts. And these measuring pins are in line with our reference electrodes. And for setup 3, this experimental setup is to provide voltage larger than 5 volts. And that is because the Arduino cannot supply a voltage that is larger than 5 volts and it cannot measure the voltage that is larger than 5 volts. So in order to measure the voltage, we have to use a digital multimeter. And this is our theoretical, this is the design to generate from our experimental data. And if we plot the 42 data points we would get from experimental 1 into data, and we use the contour function to plot our potential lines, then we would get graphs that look like this. And our expectation for the theoretical equipotential line is that of 2 electric charges with Coulombian circles at the radius of our electrodes. So we set the voltage of this line to 0, and we set the voltage of this line to our supply voltage. And here's our observation and our expectation. You can see that in our expectation, the potential at the midway between the electrode should be half what we supply. But in our experiment, you can see that voltage is 0.56, which is much smaller than 0.99. And also, for the voltage that is closer to a higher potential electrode, the voltage is smaller, that is 0.8 for our experiment, and 1.5 for our expectation. And in order to see what might cause this deviation in voltage, we have to observe how the equipotential line changes with time. So this is the voltage we measured with our experiment setup 2. And this is the voltage change with time for pin 5. This is the voltage change with time for pin 0. Pin 0 is the closest pin to our reference to the cathode. And you can see that voltage decreases for pin 5 and increases for pin 0 until it reaches equilibrium. Also, for higher temperatures, the voltage reaches equilibrium faster. And for higher temperatures, there's less voltage change. Finally, voltage reaches equilibrium value faster at pin 0. So our explanation for what causes this change in voltage is the electric double layer. It is called the double layer because a compact layer of ions is first chemically absorbed onto the surface of the electrode, and then a second layer of ions exists in the bulk of the solution. And this distribution of ions causes a potential drop. So the distribution of ions can be modeled by the Boltzmann distribution. And after we plot this into a Poisson equation, we can get the the electric field as a function of the distance to the electrode. And here you can see that when the applied voltage is increased, the electric field and the rate for the voltage gradient also increases. And when the temperature increases, that is T right here, the voltage increases. And when the ion concentration increases, that's L here. When the ion concentration increases, our voltage gradient also increases. And according to this theory, the electric double layer, which we will call EDL from now on, actually shields all of the voltage from our applied electrode. But the range it applies is in the range of millivolts, which is very small. And most potential drops occurs at a distance of micrometers from the surface of the electrode. And in our problem, in our experiment, the scale of the liquid tank is in centimeters, and our applied voltage range is in the scale of volts, which is very large, and is much larger than microvolts. So our hypothesis is that there exists a threshold voltage that the EDL does not cancel out all of the supply voltage from our electrodes. And if we apply a threshold voltage, if the voltage we apply is beneath the threshold voltage, then we won't be able to get measure anything. But if we supply a voltage that's higher than the threshold voltage, then we can measure our potential line. And also, EDL does not cancel out all of the voltage we supply because it does not go on indefinitely, and that is because ions diffuse. And finally, there may also be EDL on the detector and liquid interface. So this is a graph showing how the voltage changes from with respect from the distance from the cathode. And you can see that for higher voltages, the slope is larger, and the potential change at the N5, which is the pin closer to the higher potential electrode, is larger than the potential change for pin 0. And you can see that when the supply voltage is lower, the lines become flatter and flatter, and that is because the EDL shields some of the voltage we supply. So from here you can see that there exists a threshold voltage, and that is about 1 volt. And our explanation is that if there's no EDL on the reference electrodes, then the potential will look like this line. But if there's EDL on both the lower potential and a higher potential electrode, then the EDL will rotate like this. But also because there's EDL on our reference electrode, then the detectors, the EDL will shift down entirely, and that will make the voltage change of pin 5 larger than the voltage change of pin 0. So this is the equipotential line for 75% ethanol, which contains less ions than water. And you can see that this equipotential line matches our theoretical prediction better than water does. And from this we can conclude that the effect might be caused by ions. And here is the voltage change of 95% ethanol with respect to time. And you can see that it stays relatively constant. It does not change with respect to time. And when we added ions into our solution, we can recreate the voltage change phenomenon. From here, we can conclude that the voltage change is caused by ions. And we also want to see how the concentrations of ions can influence the threshold voltage. And our theory is that if the voltage we supply is beneath the threshold voltage, then we won't be able to measure anything. But if the voltage we supply is larger than the threshold voltage, then we will be able to measure our potential line. And this is the result for pin 5. And you can see that this is the gray dot is the voltage of our 95% ethanol without adding ions. And the blue line is as ions added to it. And you can see that its x-intercept is larger than the gray line, than that gray dot. So from here we can conclude that increasing the ion concentration increases the EDL effect. And we can also confirm the existence of the threshold voltage. So, for conclusion, double layer is the main cause of the difference between our expectation and our experiment. And it develops on a scale of seconds, which is observable in our experiments. Also, there exists a threshold voltage. And if we apply a voltage beneath the threshold voltage, then nothing can be measured. And this differential voltage increases with ion concentration. And we can control differential voltage by adding ions into our solution. The effect of EDOS has on its vector and liquid interface is that all of the vector voltages are decreased. And finally, for higher temperatures, there's a faster EDO formation because the derivative speed of the ions are faster, and there's less EDO voltage drop because the effect of fusion is also larger. And here are my references. Thank you.
Okay, thank you for your presentation. First, I would like to ask, how did you fix your pins?
How do I fix my pins?
Did you just fix them vertically?
Vertically, you can see here in, yes, they are fixed vertically again. Only one part is fit, a very small part is fit into the wires.
Okay, then would you move on to the next page?
Yes.
Oh, okay, so you use graphite as your electrical material.
Yes, that's my supply, that's my supplying, as my reference electron.
Okay. And would you please turn to page 11? Yes, the orange line and the gray line right here intersects.
Yes.
So do you think that this is a possible, this is an error?
Of
Do you think this is a normal experiment?
that is a normal experimental result.
Okay, I
but
understand. We can discuss it. Okay, then. And for my. Okay. Could you explain what TD is?
Oh, TDA stands for total dissolved solid. So it is a measurement of how much ion is dissolved into our tape.
So, please turn to page 8. Yes. Okay. So, could you explain what required is?
Oh, so this number here represents the applied voltage.
Okay. So, but on the right, you only show 3.7 volts.
Oh, yeah, that's because there's not enough space on this.
Also, you also experimented with 5 volts.
Yes, we experimented with many different voltages.
Okay.
Go ahead.
Okay, honored jury staff, I'm honored to take our decision today. For the summary of the report, the reporter first started with an introduction of its experiment setup, which was an Arduino barrier resistors as well as metal pins. And also, the main theory of the reporters was electric double layer, and the reporter explained that the lines of the equipotential lines have different types of condition changes. And for his experiment materials, he used electrodes such as graphite and copper, and used detectors and voltmeter, as I mentioned. And the variable in this experiment includes temperature and as well as ion concentration. And for this analysis software, he first used Arduino program, and he also used NumPy to draw out the theoretical electric potential lines. And his conclusions was that first, the electric double layer is the main cause between the expectation and the experiment. Second, while the temperature increases, the ETL drops. And third, which was not on this conclusion, was that with a very concentration of ions, there was also a more significant effect on ETL. And for the strength of the reporter, I think that the presentation was well prepared and it was full of theory, and there was an ample amount of experiment data to support or portray this theory. And however, I suggest that the reporter should increase the size for his fonts, as well as explain the ETL theory further. And now I would like to take a look back at the problem statement and see how the task was fulfilled. And the first task item group was to measure the lot of locations for the experiment, which I think the reporter did a great job on that. And second, consider different conditions for the experiments, including liquids. And I think the reporter experimented with, for example, alcohol and alcohol with NaCl. And in the end, the reporter did find out deviations, and I think that the task was quite fulfilled. And in the end, there are several missed points that I would like to discuss with the reporter. And for now, I would like to directly start the discussion with the reporter. Okay. First, in your first turn to the page of your first experimental setup.
First experimental setup.
Okay, you mentioned that you only did a little bit of your pin into the water.
Yes, you can see that here. It's the height approximately the same, just the notches, the height of the notches.
Alright, so how did you make sure that the height was approximately the same?
Oh, so the depth of the notches are all the same. So because we parse it up, looks like this. We put the board, we attach our pins into a notch.
Okay, I understand. So do you think that the depth that you dip your pin into the water, do you think that the depth that you dip into the liquid affects your experiment?
Yes, I think that's what there is.
Okay, so do you have any explanation for that?
So for example, you come to the left one. Because the entire thing collects electricity, and let's say this is surface water, and this is our electrode, this is electrode, and we dip our entire pin into the water, then the distance from this point to this point will be different. So intuitively, the potential at this point will also be different.
Okay. So do you think that different depths, by putting the metal pin at different depths, yields different equipotential lines?
Yes.
Okay, so have you ever thought about trying experiments on that?
Yes, we have thought of that, but in our experiment, the results didn't change that much. It only changed a little bit, and we don't have theory to describe it because to describe.
So I would like to ask for the results you got. When you dip into the water deeper, did the electric potential increase or decrease?
It's different for it decreases for some points, it increases for some points.
Okay. So now I would like to ask, do you think that the increase in the contact area of the metal probes also increases reading again?
You mean like if I cut the set, I get the electrons enter to the liquid?
In other words, do you think that the contact area of the metal probe and the liquid is a variable?
And the depth is controlled.
I mean independent. Do you think that it is one of the variables that you always experiment?
Yes, because yield depends on the surface as well.
Okay, so I mean that for now we don't discuss EPO and we only want to discuss the contact area.
Yes. So are you asking me my initial expectation or my theory after I did my expected experiment?
The reason why I asked this question was because that in my experience, when I increase the depth of the water, then the electric potential increases. And so I was curious that whether you have the same experiment.
No.
Okay. Then I would like to move on. Okay, so you also use copper as your electrode, am I correct?
Copper as my detector.
Yes. You look at electrode materials is copper.
Oh yes, but this is not included in our experiments.
Okay, so if you use copper as your electrode, do you think that as time goes by, due to the copper ions will dissolve into the water, do you think that it will increase the concentration of ions within the same?
I think that depends on the voltage we supply. So if the voltage, because when you're saying that the copper dissolves into the water, and that is the counts as chemical reaction, right? So chemical reaction depends on current as well as voltage. So if the ion concentration is large and it helps with the chemical reaction, then there will be a lot of copper that dissolves into our equipment. But for the voltmeter, if you're asking about the detector, then because the current through the voltmeter is very, very small, so very small amount of ions is dissolved.
Also, so you neglect this effect for the voltage.
Because the current in the voltmeter is small.
So, and for my next question, you also add NaCl to the zinc.
Yes.
So, do you have any idea what would happen if you put NaCl in? Have you considered the effect of electrolysis?
Electrolysis? We have not considered the effect of electrolysis because in our experiment we couldn't observe any hydrogen gas forming. So there are bubbles on our applied electrode.
So, do you think that is there any possible that, for example, chlorine is a sort of gas, right? So, do you think that is there any possibility that the gas molecules would attach to the metal electrodes?
To the metal electrodes, there might be.
Right. So, we haven't tried experiments.
Try to detect chlorine that is attached to our electrode.
I mean, to determine the effect of the adhesion of gas molecules on electrodes.
No, it's not visibly observable. So we did not do experiment on that part.
So, if you increase the concentration of your NaCl, do you think that it will have a more significant effect?
If I increase, you can see that the TDS for my NaCl is actually not that large. So if I increase my NaCl concentration to a really, really large value, then it might have an effect on the
The reason I asked this question is because in my experience, I tried with 0.1 amp, which means that I added a large amount of NaCl into the zinc, and I could clearly observe the generation of chlorine around the metal electrodes, and I Yeah. Now, for my next question, I think in one of your experiments, the temperature was 5.6 Celsius.
Yes, it is.
This one. So, could you explain how exactly you control the temperature?
We put our potential light into our fridge. Yes.
So, okay.
Yeah.
So, now, okay, so, you mentioned about the effect of temperature.
Yes.
So, could you explain why the temperature affects the electric potential with ETO?
Also, first of all, let's first examine how EDO develops with respect to time. So, EDO develops because the ions have been moved to the electrode to accumulate there. And for higher temperatures, the drift velocity for the ions is faster, so the expected time for the ions to accumulate should be shorter. So that is observed here. For higher temperatures, the time it takes for the EDO to reach equilibrium voltage.
So, do you think that the temperature affects the integration rate of the ions?
Yes.
And I guess that's all.
Can you please start to summarize the discussion?
Okay. In my discussion with the reporter, we first discussed about the possible effects of an increased contact area between the metal probe and the liquid. And according to the reporter, he didn't find that to be much of an effect. So, no further discussion will go. And furthermore, we move on to discuss whether or not the copper ions that dissolves into the water seeps affect the potential. And then the reporter explained that it is related to the voltage that is supplied to the water seep. And so that due to the amount of voltage in his experiment, so that this effect was not significant.
Okay, no, the reviewer, next question.
What is the definition about the radiation?
That is the formation of the electric double layer.
Can you quantify it?
Can quantify it? No. I can measure it experimentally.
Okay, about the opponent and the reporter. What is the main cause that is the radiation?
Isn't that the last question?
I mean, what is the main that cause the radiation?
That is the existence of ions.
Okay, then what are the consequences?
I think according to the reporter's experiment results, it is due to other reasons.
So you agree with the reporter?
Yes.
Okay. Do you think that the airflow will influence the electricity equipment line?
In airflow above the water.
I mean, if there is some airflow into above the water.
Yes.
So, okay. And in your theory, do you consider about the boundary condition that we cannot use about it?
Well, why with the boundary condition, we still use our theory because the potential is caused by the potential we established in the potential will be the same. So as the potential we established in boundary set for the existence for the effect of ions.
Okay. If the electrical conductivity is increased, that will it affect the exploitation and the deviation?
Will that affect my PhD? Yes.
How will it affect?
So it doesn't affect my expectation and experiment if there is no ions in the solution, but because there are ions in the solution, an increase in the permittivity will cause the I can show you in my presentation, an increase in the present.
I want to ask what the opponent is. If you increase the electrical conductivity, then what will affect the experiment?
I think first with an increased conductivity,
You're using the higher voltage you measure will be higher.
since it affects the concentration of ions, perhaps. So I think it will perhaps also affect the concentration.
So when the relative permittivity increases, and that is key R here, the voltage gradient
So
decreases.
it will decrease.
Yes.
Okay. If the two electric is the two contact is very close, then how will it happen?
Then what will happen?
The equivalent type.
Okay, now, the reviewer should be here for your.
And the common statement is place two electrodes into water and supply a set voltage and use a voltmeter to determine electric potential at various locations. And investigate how the mixture equipment line deviates from the expectation for different conditions and liquids. And I think the main focus should be the expected condition for the equipment line, and how the different liquids affect the equipment line and what causes to deviation. And for the reporter, that he shows the phenomenon about his exploitation, and he compares, did a compare between the theory and he has his exploitation. And about the theory part, he using the EDL to measure it, and also for the experiment part, the reporter changed many parameters about like the temperature of the liquid, and he changing different liquid, and he changed the voltage, and also he changed the potential. And what the reporter did well is he will control the initial condition, and he shows a comparison of situation and the experiment result. But what the reporter didn't think about, he ignored some reason that may also cause the deviation, like the airflow or different items. And also he didn't have a well quantitative explanation, and he didn't have a theory line. And he lack of parameters like the height of the liquid and the shape of the voltage. And this is the outline about the opponent. The pros for the opponent, he point out the unclear explanation about how the EDL affects, and he mentioned a deviation that may cause by depth of the point. But the opponent didn't do well. He mentioned the result and investigate in his experiment, and he didn't ask about the theory limit, and he didn't discuss a way to quantify the deviation. And for the discussion, the opponent asked, do you think the result of copper will affect the deviation? And the reporter said it is no. And I agree with the reporter because that the activity of a copper is known that the iron will be very, very small, that it can be ignored. And then they discussed about the gas molecule. And I agree with the opponent that this factor could change the result. And also, I asked about the reporter that for the airflow that will result the experiment, and the reporter means yes, but I think the airflow is on the surface of the water, so it will not affect the experiment result. And this is the point based about the opponent and the reporter. First, he showed another reason may cause the deviation, and the lack of the parameters like the height and the different electrical conductivity, and the shape of the electron and the material and the radius that will affect the experiment result. And
No, thank you.
So for concluding remarks, the opponent asked me that when we take the electron into the water affect my experimental results, and I want to clarify that it will influence every volume, so that's why we kept it constant. Also, your opponent asked me whether the copper ion that is dissolved into the pig may influence my experimental results, and I have to clarify that because the current drilling voltmeter is very, very small compared to the total amount of ions in the change. This effect is also very, very small. And for electrolysis, no bubbles were observed. And when we supply the voltage, we need the necessary voltage to form electrolysis. There's still the voltage change phenomena can still be observed. So we don't think the change in the voltage is primarily caused by the formation of gases and attachment to our reference electrodes. And we have one suggestion for the opponent, and to try not to cite your own experimental results as part of the TYPT component goals to help me reach a conclusion with my own experimental results. And to reply to the reviewer, we cannot use the previous theory of the EDL to quantitatively describe our experiment because we discovered the threshold voltage. And you mentioned in your review that we did not change the conductivity, but we did change the conductivity by adding ions, and this changes the total dissolved solar, and that is measured by conductivity. And that's the concluding remarks. Thank you.
Okay, now question from
You go to the theoretical part. I mean the equation you solve, the Poisson equation you solve. Previously. Okay. So I think you only solve. Okay. You only because it's I expect you solve the Poisson equation and then you can plot your contour line. Okay. Right? But seems like you only solve in exploration, right? So how come you can have a 2D profile of your electrical engine?
Oh, so this here is to describe how the effect of the EDOL would change drop qualitatively to these parameters. And this is the 2D profile because this is from a reference, and they use it.
I mean, how to plot your equal potential line? Because you have to sub phi. That's electric potential, right? You have to solve the equation and go back to previous one. Okay, you have to solve the differential equation, and then you got phi, and then you plot. But here you only have one dimension.
Yes, that is true. So we did not plot the theoretical line with the effect of EDL. We did not plot it.
But when you plot this one.
Oh, this one is calculated by yes, this is our experimental
You
result.
just consider it's a point chart. You just consider it's a point chart.
Yes.
Okay. Well then, come to another problem. If you look at the expectation and your experiment, this one. So why the curvatures different? I mean, here you only talk about the number.
Yes.
Okay, but if you look at the curvature, I mean, your experimental result and your expectation is, it kind of, you can see a curvature in your experiment, right?
Can I use the blackboard?
Yeah.
So let's say this is our reference electrode for 0 volts, and this is our reference electrode for 5 volts. And if we plot the voltage as a function of the expiration, it will look like this. And the circles from here will be tighter, and that will result in these curved lines. But with the effect of PDL, it shields out the voltage from here, and it shields out the voltage from here. So the lines, the slope of the lines are less steep, and that will result in less curvature. Because the voltage change is not as steep. The steep part was blocked out by the PDL.
Yeah, I don't think that.
So I have a question for the reporter. It says that on your picture that you insert five probes in your water at the same time, and then you connect to your voltmeter and measure your voltage one by one. Is that right?
You mean
You insert this six probes
yes?
in line into water, and then you measure the voltage one by one.
I mentioned them at the same time. There are 6 pins. There are 6 analog pins for this Arduino, so that's why I have 6 measuring pins. They can measure all at once.
And all of them at once.
Yes.
So I wonder, my question is, you just insert one, and you move your probe. Do you think
Yes, we think the measuring pins might have an influence on each other.
you're including each other? So my question is, you think for opponent?
I think I have no idea what will happen actually, but yes.
You think so? You think you're including each other or not? My question is, if you just insert one probe
That's fine.
and measure the voltage, rather than insert 6 probes altogether, so the position is different. So
Yeah. If ETO happens on the pins, then placing two pins into the water at the same time will possibly affect the potential.
I think it's a voltage will change by the time that if you move the electron and you will change.
Thank you.